So we have 4 short presentations, and I think it's better to reserve 10 minutes at the end, so we can have 10 minutes more. And the first talk is about effect of policy relevance factors on COVID-19, patient survival probability, and information theoretical analysis. Timothy Mumladze and Daniel Wilson.
Can you see the screen?
Yes.
Okay. Tina and I will be presenting on the effect of vaccination policies and other relevant factors on the probability of patient death from COVID-19. Just for transparency, this research was based on previous collaborative work with other second-year PhD students at American University, so I want to give them credit where it's due. So a little bit of context and motivation. We started the project in April during the swing of the first wave. And although understanding of the disease or COVID-19 was relatively limited at the time, what was very obvious was that there was heterogeneity in the progression of COVID-19 in terms of its severity and pace. So with this in mind, our main question was, had any pre-existing policies influenced susceptibility to COVID-19? And if so, what was their estimated impact? And in order to answer that question, our objective was to estimate patient conditional probability for survival or death. So ideally, the data that we would like to have would be at the individual level and at the country level. At the country level, this was very easy to find, and we collected information on prior vaccination policies, health, economic, and welfare indicators. Next slide, please. At the individual level, it was a little bit harder, and I'll discuss where we ended up sourcing it from. But we were able to, in the end, get information on age, gender, country, outcome, and pre-existing conditions, but we didn't have enough observations with pre-existing conditions, so we did not use this. So we were able to access data from the Open Access COVID data group, which essentially used big data techniques to collect information on individuals throughout the world. Unfortunately, towards the end of May, their uploads began to reflect their need for quantity over quality. And so the data set ended up being more of a count data set of individuals who had gotten COVID and their geographic location. So the marginal return to additional extracts in terms of that information that we needed at the individual level, which included age, gender, country, and outcome, was very small. And so our sample size ended up being about 500 individuals, and we stopped collecting data around May. So with these limitations in mind, our covariates were moderately correlated amongst the few that we did have, and amongst the sample, the ratio of death to infected was relatively low compared to other outbreaks of other diseases. So our modeling approach is an information theoretic one. It has the following preferred properties that I'm sure this audience is well aware of, but is especially and was especially beneficial in our circumstance with this very limited data set at the individual level. Next slide, please. So our model was as follows. We were trying to determine the probability of death based on gender, age, BCG vaccination policies, immunization policies with respect to measles and hepatitis B, private health expenditure per capita, and the mortality rate attributed to air pollution because COVID-19 is a respiratory disease. So on to the results. The marginal effect of this primary model is as follows. The largest marginal effect was with respect to or came from the BCG vaccination policies. An individual who had lived in a country that had never enforced or implemented a BCG policy, vaccination policy, was about 47% more likely to pass from COVID. The biggest critique that we got from our model was that these policy variables could be instead proxying for other healthcare or systematic variables within a country. We tried to implement variables regarding, or tried to implement information about universal healthcare, but the definition in the literature about what a universal healthcare system is per country is a little vague. And when we tried to implement a variable, we had absolutely no variability in our samples, so we excluded it. We ran an additional model just for robustness that did include a centralized healthcare dummy. This is different from universal healthcare, but it was the best that we could do. with our limited sample size. And when we included it, it was not statistically significant, and the marginal effects of all the policy variables remained relatively the same. We did run a third model with including the positive rate, but not all countries revealed their positive rates of COVID at this time, because the last data collection that we did was in May. And so I can discuss it later on the presentation, but we didn't include it for analysis.
Thank you, Danielle. The next step for us was to incorporate prior information into the analysis. We know that priors usually come either from theory or independent data. Given the nature of the question we were studying, we had to rely on the independent data on severe acute respiratory syndrome as a prior information for COVID-19. And we chose SARS because it is the virus which is closest in nature to COVID-19 virus. So the priors we're including are patient probability deaths that exclude medical personnel, and they are reported in the table you see on the slide. Unfortunately, the age groups that we have here are quite broad, but we couldn't get more detailed distribution of death probabilities. Overall, death rates are increasing, death probabilities are increasing in age, and on average, male patients are more likely to die from SARS compared to female patients at any given age. This slide reports marginal effects of covariates on the dependent variable. Results in blue are for the model without priors that Danielle has already covered, and results in yellow are for the model with priors in it. So both models produce relatively consistent results. The marginal effects are reported at the sample mean, which is given by a 52-year-old male from the country with current universal vaccination policies. So the most pronounced result that we see here is the one for BCG variable. So first of all, we observed that individuals from countries that never had universal BCG vaccination policy are roughly 50% points more likely to die from COVID compared to individuals from countries that do currently have a universal BCG vaccination policy. On the other hand, we also observed that individuals from countries that did have universal vaccination policy at some point in past are only around 20% points more likely to die from COVID. Other important policy variables that we identified are air pollution rates and health expenditure. Marginal effects on those have anticipated signs, and they are statistically significant. Marginal effect of the age is positive as expected, and the marginal effect of gender is negative, meaning that females in our sample are roughly 5% points less likely to die from COVID than male individuals. Next, we wanted to evaluate the predictive power of our model. We did it by plotting the predicted probabilities of both models against the actual data. We can see that both models do a very good job at predicting probabilities. However, the model with prior information, which is given in yellow, does relatively a better job. And finally, we conducted country comparisons. We wanted to select countries that were similar in many aspects, but differed in one of the policy variables. The first country groups that we will look at are US versus Australia and Singapore. The three countries are very similar to each other in terms of their air pollution rates and private health related expenditure. However, they differ in BCG vaccination policies. US never had a universal policy. Australia did have it between 1950s to 1980s, and Singapore does have it currently. If we look at the differences between US and Australia in terms of predicted death probabilities, we see that the differences are almost zero at younger age. The gap in predicted probabilities increases as the age rises, and we see a relative convergence in predicted probabilities at the highest age groups. If we compare US to Singapore, however, we see that the gap between the two countries is even greater than the gap between US and Australia. And we do not see even a slight convergence in predicted probabilities at the highest age group. So if we calculate predicted probabilities of death at the means of the sample for each country, we will see that the predicted ratio of death rates between US and Australia is equal to 7, and the same ratio between US to Singapore is roughly 72. If we calculate the same ratios using real data, we will find that the ratios are roughly 4 and 72 respectively. So the model did a very good job at predicting the death probabilities. Finally, we will look at the comparison between US and Philippines. These two countries are drastically different from each other. US, as I've already mentioned, never had universal BCG vaccination policy. Philippines does have it currently. However, Philippines also quite the opposite of US in terms of health expenditure and air pollution rates. Regardless of those differences, we see that the distribution of predicted probabilities is quite similar for both countries. And we attribute this similarity to the fact that it's not only the BCG variable that is important in explaining the outcomes, but also health expenditure variable and air pollution variable play an important role when explaining the predicted probabilities of death from COVID-19. And finally, calculating the predicted ratio of death rates between US and Philippines gives us the ratio of 1.3, while the real data gives us the ratio of 1.6. Again, we conclude that the model did a good job at predicting the death probabilities. So to summarize, we used information theoretic inferential approach to study the effects of pre-existing policies on susceptibility of COVID-19. Our analysis indicates that there are 3 potential policies that can improve patients' conditional survival probabilities. These are a universal BCG vaccination policy, air pollution, and health-related expenditure. Additionally, we also find that the effects of each one of these policy variables are magnified with age. And finally, the analysis could benefit from further analysis, and the possible extensions could focus on re-evaluating the results as more data becomes available. We would also like to control for more demographic characteristics as well as the pre-existing medical conditions in order to see if the results of the model are persistent. Thank you.
Thank you. So the next talk is about big data, data quality, and entropy. Proposal for data quality analysis of digital platform is Irene Bardi.
Okay. Let me know if you see.
Yes.
Okay. Hello to everyone, and thank you very much for giving me the opportunity to participate in this interesting workshop. I will use my time to describe the project that I was involved to for my master thesis. I had the opportunity to do my master thesis at Orza Group, an Italian company working on information and communication technologies. I worked with the project team in charge of managing data for a specific client, Telepass SPA, which is an Italian company operating in the mobility field. The aim of the project was to evaluate the quality of the data platform, and which can be defined as big data. So firstly, I analyzed the big data phenomenon, then the data quality question, proposing an innovative approach with using the concept of entropy. All started with the information explosion. We went from a situation of lacking access to data to the complete opposite, that is an overabundance of data. We are nowadays flooded with data, as we can see from what happens every 60 seconds in the web. This sudden growth required the introduction of new unit measures for data volume, for example, the zettabyte. To make it more explicit, 1 zettabyte is the equivalent of a pile made of 250 billions of DVDs, almost the distance between Earth and the Moon. We reached the first zettabyte around 2010, and since then the data continue to grow dramatically, and it's forecasted that in a few years the amount reached will be of 173 zettabyte. This phenomenon has been called big data, and its definition remains slightly ambiguous. It's in fact a common practice to define it through its properties, which have been added over time. We went from the 3-bis definition to the 4-bis definition given by IBM to the 6-bis definition of Microsoft. But the question is, why are big data so important? They are important because they are the base of what is called the data economy. Data is a resource that needs to be extracted and elaborated in order to produce value. This process is called big data analysis and provides the revelation of correlation insights, forecasts, algorithms, and so on. But the degree to which data can be used is largely determined by their quality. This means that the presence of high-quality data is a necessary condition for guaranteeing the extraction of value from the data and the accuracy of the analysis. To evaluate the data quality has been created a reference framework that contains dimensions and elements as a base for the analysis. And here we can see some of the causes that can have an impact on the data quality and some of the possible ways to improve it that I also applied in my work at Orsa Group. But something on which is necessary to pay attention is that speaking about data does not necessarily mean to speak about information. As we said, having a big amount of data does not ensure the efficiency of its use. So what I proposed in a change of perspective is a change of perspective. That means that we have to focus on the quantity of information contained in the data rather than on the quantity of data itself. And the question is, what to use as a measure for information quantity? So I saw the work of a professor, Ariel Goichenske, I think. And I decided to use the entropy, the concept of entropy, which is defined as the average quantity of information contained in a sequence of data. The concept is one of the most important features of the Shannon's information theory. So I used the 3 different types of entropy, which are the maximum entropy, the joint entropy, and the conditional entropy in my work. During my internship, I had the opportunity to apply both data quality, traditional data quality measures, and the entropy ones on the data platform of Telepass, of which we can see here a schema based on the 2 main elements that are a relational database on premise and a data lake on cloud, and their channels. In particular, the project involved the use of 5 instruments: the Talent Data Catalog for the activity of cataloging and metadata management, Apache Hive, which is the data lake itself, on which we did queries and data extraction, NiFi, Apache NiFi for the analysis of flows, and then RStudio for the entropy analysis and the data manipulations. And then at the end, ClickSense for creating a dashboard for monitoring the data quality. Here we can see some examples of the analysis that were done, like imputation, anomaly detections, and one example of the entropy analysis. As a conclusion, in my work, I did an overview on the big data environment, making a focus on its data quality. And as a result, I discovered that the combination of classical techniques and the use of entropy allows a broader view of the data quality measures. Thank you for your attention.
Thank you, Irene. So the third work is about an informametric approach to estimating the supplemental poverty rates of public use microdata areas by Danielle Wilson. Thank you. No, the microphone, please.
You're on mute, Danielle.
Sorry, there you go. Okay, so I'll be presenting on the use of an empirical application of infometrics on estimating the supplemental poverty rate of public use microdata areas, also known as PUMAs in the United States. So what is the supplemental poverty measure? Unlike the official one used in the US, which is characterized as being somewhat crude, just a multiple of what your housing expenditure is, the supplemental measure includes the necessary expenses that one needs to live on a regular basis and any additional government subsidies one might receive in their family. So the more official definition in equation 1 and 2, an individual is in poverty, according to this measure, if their resource summation falls under a threshold defined by the Bureau of Labor Statistics, which is adjusted for an individual's family size and geographic location. And an individual's resource summation includes all of the components that were in the previous infographic. So not only family cash income, but any necessary expenses and government subsidies. So in its official capacity, the supplemental poverty measure uses the Current Population Survey's annual social and economic supplement. This is one of the more popular surveys within the United States. Its supplement asks for very, very detailed income data that other surveys don't ask for. And the sample size of this survey is about 120,000 observations. That is relatively small, and consequentially, estimates, regardless of whether or not they're poverty or others, can only be produced at the state level. That is the most disaggregate level that the survey can produce estimates for, which is a drawback for those interested in policy estimates or policy measures at a more micro level. The American Community Survey, or the ACS, is a larger sample, or has a larger sample. It's about 3 times the size of the previous survey that I discussed, the CPS-ASAC. The benefit of it is not because it's large, it can produce estimates at the public use microdata level, but the consequence or the drawback of this survey is that it's missing a number of key data elements required to produce the supplemental poverty measure. Last year, Fox, Glassman, and Pakas published a working paper detailing how a researcher could use just publicly sourced information to impute the necessary components in the supplemental poverty measure using the American Community Survey, so that larger survey with less accurate information. Just a recap of the pros and cons of both surveys. In the CPS-ASAC, there is more detailed income information, but the sample size is relatively small. But in the ACS, the sample size is larger and can be used to produce state and PUMA estimates, but there is less detailed information and requires additional imputation. The consequence of this can be shown in the map. So if you're using both surveys to produce poverty estimates at the state level, there are large differences, up to 4 and 5%. And considering that poverty estimates range from between 10% to 20%, 4 to 5%, or even 2% is a large amount. So what can be done? So given that the CPS-ASAC, or the supplemental poverty measure and the American Community Survey requires more imputation, why just throw away or disregard more accurate information from the CPS-ASAC? So inspired by Papalias and Fernandez-Vazquez, information theoretic approach to count data, I will similarly use disaggregate estimates at the PUMA level and constrain them with additional information at the aggregate level from that CPS-ASAC, so that more reliable survey. Here is another comparison of what's actually observed in each survey. So in the CPS-ASAC, or the more detailed but smaller survey, you directly observe 5 components identified with blue stars. So family cash income, child expenses, medical expenses, energy subsidy, and SNAP. There is additional imputation, it's imperfect, but some of those components that require imputation use administrative simulations or simulations that use administrative data. So they are still relatively better than the imputations in the ACS. In the ACS, however, only one component is directly observed, and that's family cash income. All the other components require imputation, so it's relatively less reliable, or there's relatively more noise within this data set. So here's a small infographic trying to communicate the how I constructed my main constraint in my infometrics model, which I'll describe later. So at the state level, which is identified by this very large box, you can observe the state poverty rate using the CPS. You can also observe the state poverty rate using the American Community Survey, that larger, less accurate survey. But you can also observe the poverty rate, that's noisy, at the PUMA level within each state. You can write the relationship between these two rates as a weighted average, but I'm particularly interested in the poverty rate at that micro data level. I'm going to write the observed poverty rate in the stamp using that survey data as a function of what is true and unknown, that true and unknown rate, and the relative error or noise from the additional imputation mu. Substituting that back into the weighted average equation or relationship, instead of using that piece of information at the state level from the less reliable survey, I'm going to use the more accurate piece of information from the CPS ASET, that survey that asks for additional detailed income data. So essentially, I'm using a more accurate piece of aggregate information to constrain the less accurate pieces of information. The goal of the infometrics model will be to estimate that relative noise from the imputation. And just for transparency, it's imperfect, but it is better than what is currently just observing it and using only the ACS or that less accurate survey. Just for those who are unfamiliar, if there is anyone or any students, any error in the infometrics model needs to be redefined in a discrete term. And I used to define the support space that standard errors from the estimates themselves. I use plus or minus 10 standard errors, but I do various robustness checks with different estimates of standard errors to show that even smaller ones up to plus or minus 4 standard errors are robust, and the estimates are not statistically significant from those that I'll be presenting here. So this is my X maximum entropy model. I'm maximizing entropy subject to that constraint that I previously walked through and normalization constraints. So what's coming out of the model? I'm getting estimated weights for my support space, and I can use them to estimate the relative noise. I can then convert that relative noise into its percentage point form and then subtract it from the supplemental poverty rate that is observed in the American Community Survey. When I do that, I get a refined supplemental poverty rate. What does that look like across the states? Well, the difference in that estimated refinement, what I'm calling, that mu hat, is shown in this map. There is substantial variation, and about 75% of those PUMAs that are 3 standard deviations above the average, which is about 2.5, are in Rust Belt states. I don't talk about that further, but it's something I look to explore later on. So the biggest concern is that there's a pattern amongst whether or not it's space or population, but there's a pattern driving the estimated or the magnitude of that refinement. So what I do is I plot the area by the magnitude of the refinement on the vertical axis. I show that, or as one can see, the correlation between area and the percentage point or the maximum entropy refinement is very small. I'm interested in area because all areas or all PUMAs have about 200,000 to 300,000 people. So PUMAs with a very, very small area are likely to encompass regions that are closer to urban states or urban regions, and PUMAs that are larger are likely in rural places. So there's no pattern that I need to be concerned of. Just to double check, I run a model. So the dependent variable is the magnitude or the entropy estimated magnitude of that refinement. And I include for my covariates variables that are used not only in estimating that refinement, but also area. So the components that were used to estimate the refinement were population and the initial supplemental poverty rate directly observed from that less accurate survey, the American Community Survey. I use various different regional controls, but the most important that I use is the state controls. The state controls, compared to just using census regional controls such as West, Midwest, South, and Northeast, does a better job at eliminating a substantial amount of that prediction error, but the errors are very, very heteroscedastic, suggesting that there's possibly omitted variable bias. In that case, that's okay with me, because that signals to me that the components used in my model, so the covariates, aren't perfectly explaining by any means the maximum entropy estimated refinement, and the magnitudes of what they're estimating are very, very small. So conclusion, why is this useful? Essentially, the infometrics approach allows for the reconciliation of the same type of information just coming from different sources. Each survey, the American Community Survey and the Current Population Survey, has its pros and cons, but in one model, I use the pros from both, and I produce a refined supplemental poverty rate. Of course, this refined rate is going to be imperfect, but it is a better alternative to what is just simply observed from the less accurate survey. So it should be interpreted as a conservative alternative poverty rate that provides additional information that one could use when doing poverty analysis, especially because these PUMAs can be crosswalked to the county level. That's it.
Thank you. Okay. So the last speaker is second B1. Sorry for any mistake. B183, and his talk is about introduction to non-extensive cross-sec entropy for social phenomenon modeling. Thank you. The microphone, unmute your. So you can start. Okay. Thank you.
Okay, then my presentation is Introduction to Non-Extensive Cross Entropy for Social Modeling, Social Phenomenon Modeling. The essence of my presentation is rather methodological than empirical. Of course, application of this method can be found in most of recent publications, and as I will give you at the end of this presentation. Okay, so let me, something is wrong with this. Okay, so non-extensive entropy econometrics.
Sorry, second.
Yes.
Did you want to share your screen? Do you have slides? Are you showing?
Yes, I have a slide, yes.
Yeah, so you want to share your screen?
Okay, let me.
That's it. Yeah, thank you.
Okay, thank you.
Should be the green button at the bottom of the screen or the top of the screen.
Yes.
Share screen.
Yes, yes.
There you go.
Is okay now?
It's there. It's coming up now.
Thank you. Yes.
Okay. So the Thalys non-extensive cross entropy is suitable for statistical modeling of complex systems. By complex system, I mean non-ergodic system. Generally said, with the system in which microstates are correlated, present heavy Q, or generally tending to fractal or multifractal distribution. So, of course, you have a short time to present the subject, which is very expansive. I try to, in the following, to present power law. How can be applied in social sciences, in which context? I shall try to present Thalys entropy versus Shannon-Gibbs entropy. Of course, for empirical reason, I try also to present in short time Thalys generalized Kullback labor information divergence, which is just a generalization of Kullback labor information divergence based on Gibbs-Shannon entropy. Then shortly I present inference and concluding remark. Okay. Okay. Yeah. Ubiquity of power law in social science has been proved. Here I talk directly about power law because non-extensive entropy econometrics of Thalys is derived from the power law distribution. Economic and financial market, free market transactions are essentially PR driven. Anticipating market prices, intensive technology product market prices, financial return are characterized by very large deviations, variance, and average may tend to infinity too. Of course, this is just tendency. Okay. To be very short. What is the characterization of the power law related economic phenomena? This business, for example, the business about which I told, tend to be a free scale phenomena, meaning that a significant change of output is possible without input change. For example, to media, marketing, and you observe also spatial or temporal granularity, meaning that macroeconomic fluctuations from idiosyncratic shocks to film, and that's essentially PR driven. For example, in the United States, in many developed countries, where we have big firms, big enterprises, and many small enterprises, we may observe that a shock is rather not distributed according to Gaussian distribution, but according to power distribution, because the big firms will have at least, as in the United States, the study showed that 30% of shocks are generated by the 100 biggest enterprises. In Japan or in German Republic too, meaning that in this case, and the shock transmission decay according to power law. Of course, there exists also Gaussian product too. For example, the market of pizza, we know that the price, the variance is very small concerning the price. The price is almost similar in a competitive market. For this kind of phenomena, of course, it is much easier to have a sense for business feasibility study or economic analysis. In the case of power law distribution, it's much more complicated, and that is why most of prediction may not have a sense if we don't take into account of power law distribution. Then, okay. I talked about power law distribution. Here I want to show very succinctly what a power law distribution look like, at least at formal point of view. The probability of S higher than X tend to have to follow a function, power of function k multiplied by X to minus alpha. S may be the size, meaning that the probability, the upper size of a series tend to have a power law distribution. Another main characteristic to underscore, to point out here, is that the power law has meritancy properties. When you have two series displaying power law, the multiplication, addition, or any kind of combination will generate another power law distribution. Next, even when we combine power law distribution with normal, log normal exponential, we will have always the combination will provide to a power law distribution, meaning that this explains the ubiquity of power law in nature or in social science phenomena. Okay, now, of course, I would like to present here very shortly, once again, from Shannon Gibbs entropy to power-related extensive entropy. Just when we power law, as I said, generate non-extensive entropy as a model. Then when we take the three simplest ordinary differential equations, here we not present this, and we combine them, the inverse of its solution leads to the entropy, the size entropy formula. Of course, I know that I'm very succinct here to present everything, but I will give at the end the literature in which it will be easy to find details. Then here this is the maximum entropy, the Charles maximum entropy. You see that in this case, when you have Q equal to unity, we drive the Shannon entropy. But the Q, the Charles parameter, Q, is very useful. It varies between 0 and 3. And in the velocity of Q to 1, we obtain the Gibbs Shannon entropy, of course. I'm going very quick. Of course, it is also to present the Charles version of the Kullback-Leibler divergence in constraining problem. Of course, what I presented is discrete case. The continuous case is not be presented here, but also it is possible to present it because the literature gives a lot of cases of entropy, Charles entropy for continuous models. You see that here the work of Ammon, Judge, and Miller of 1996 is very helpful to suggest this model. What is done also here is that I took into account of the Charles entropy, of course, minimizing of P and R. Of course, P and R are vectors. R is the prior and P is the posterior. Then we minimize this kind of distance between there's two vectors with the moment constant U equal. I know that you are very used to understand this. The only difference is that here I use another operator related to Charles entropy. Okay. So the regular conditions as usual. In this case, I used the so-called escort distribution. Okay, now concerning the inference, exactly for parameter the significance, of course, we use the numerator where is the computed calculated entropy of the system, and the denominator the highest maximum entropy of the system out of restriction impact. Cut the number of parameters is and number of subspace points. Okay. Now the application. Sorry, here it is not working, but let me use this. May take a lot of time. If we generate the example.
So a few minutes and then we start with questions, please.
Yes. Thank you. Okay, it is. In the example that I presented in this case, we have to reconcile conflicting cross-border data source for updating national account using this cross-entropy economic approach. We have official data from survey and data from sensors at the border between Germany and Poland, and combining this data, we found the distribution of cars, vehicles, according to the type of vehicles and according to the origin of these vehicles. Yes, it is possible to read the war model. Okay, let me come back to the presentation. Where is it? Sorry, because I don't use this. Okay, yeah, I have here is the application. We have countries, we have type of vehicle, bus, truck, cars to 15 persons, and so on. We had just only the totals by column and by rows, and by rows we have the total from detectors, and the total by row is found from detectors, and total by column. Yes, this is the total by column is coming from survey study, and we generated information from concerning which kind of type of vehicle and from which country, knowing that information from a detector when distributing power law distribution. It is not okay. Okay, let me now finish. Yes, non-external cost entropy could be a hope for testing a new economic paradigm to which seems better appropriate to the ubiquity of power law. It can judge complexity level of any system to the size Q parameter, because when Q parameter is not equal to unity, it happens most of the time. For example, for financial data or many other data, this means that we are not dealing with Gaussian distribution, but with another type of distribution which is much more complexified. Charlotte's entropy combined with Bayesian philosophy are strong enough to better solve behaved investment, non-linear problems. But anyway, we find there is many problems when on computing point of view, and we hope that a two-parameter size entropy formulation will be found so as to improve model estimations. Thank you for your attention. I know that I have very quick, for literature, for example, here I just give the main literature. Here is my book published 2 years ago. And Gabe also has inspired this paper. Of course, Mr. Golan and colleagues, Ikeda and so on. Of course, when I presented this paper, I have no time to prepare a much more interesting paper because it was at the end of the deadline has passed, and I tried to find something just for a fast presentation. Thank you for your attention.
Thank you too. So, any question, comments?
Yeah,
For the speakers.
Okay. Shall I go, Rosella?
Yes.
Okay. Just one fast comment on the last paper presentation. Second, it's very interesting. However, I am not convinced yet, and we don't have to talk. We don't have time to discuss it much, but it's something to think about. I'm not convinced really that the Salis entropy is designed to do estimation in the sense that you're doing it. Of course, technically it is possible, but remember that it doesn't satisfy some of the fundamental properties of Shannon entropy that are necessary in order to do a good inference. So it's just a comment, it could be a bit philosophical, but this would be just my own understanding of Salis entropy.
Okay. I have some question for the first paper, and the third paper is the same. The question is about if you consider some spatial variables or in your analysis or not.
If I consider, sorry.
No, it's for Tinatin. The question is for Tinatin and for Daniel Wilson for the first paper. Okay. Have spatial variables being considered in the analysis?
No, in our COVID paper, we did not consider including any spatial variables, unfortunately.
Because in a similar application for, in Italy, we find some good results for pollution, this kind of variables. So I see that you consider this determinant, so maybe would be.
I agree that would benefit the model a lot, but I think everyone should keep in mind that we did this paper, we worked on this paper almost a year ago, and back then we didn't have access to a lot of data.
Yes.
So we
yeah.
kind of had to work with what we had at that time. But I agree that as time goes, more and more data becomes available. So definitely that would be something to consider in update of the model.
And for the Irene, just some idea about the gain, the benefits in considering missing data. If you, in the future, maybe you can add this kind of just.
Okay. Well, in my calculation, I did not consider missing values. So it could be interesting in the future to include them in the analysis and see the results.
Okay.
Yes, please, if I can say something about the very useful Amos comment.
Yeah.
When I started to use the Saris entropy, I was theoretically expecting to retrieve the same output as the Shannon entropy, the cross entropy, because I was using the normal distribution data set with displaying normal distribution. Yes, when I used this Saris entropy, I tried exactly the same values. But when I used the same methodology of Saris to analyze financial data, the financial return, or some growth model, which exactly by testing were displaying the power law, I found differences in output. This is simply because power law is a nonlinear distribution able to display fractals. And we know that fractals can be found even in low frequency data. So only in this case, I found differences. In many other cases, Shannon entropy and Saris entropy leads to the same output. So this gives me some foundation, motivation to continue research on basis of this previous result. Okay, thank you. That is just my comment. Of course, the research is undergoing, and I try to find.
Yes, thank you. We have some questions for Irene and for Danielle, please.
So the one question I see is, why did Singapore and the US have such different death outcomes? That our conclusion was that it was a combination of policy factors. So it was their vaccination policies and their air pollution. And Tina can expand more on it. But.
Yes, sorry. So US and Singapore were similar in health expenditure and air pollution, but then US never had the universal BCG vaccination policy, and Singapore currently has it. So we attribute the differences to the difference in vaccination policy, basically, because they are similar in other policy variables. Relatively similar. I think they are at the top of our sample.
Thanks.
The question for me is how much bad data is there? Where the value is mostly in structured data than in unstructured data, and the structured data are just the 8% of the global amount of data, so a very low data are considered good data.
One of the problems with bad data is coming from legacy systems. So if you've got a lot of old equipment, a lot of old machinery, an old production facility, then you probably don't have good data coming from it. I don't know if you want to respond to that.
Yes, okay. So, okay. So now I would like to thank all speakers for the informative contribution. Thank you so much.
Thank you.
Thank you.
I thank you very much.